Hi guys, and welcome to this online tutorial for electromagnetism. This tutorial is intended for students of UCD taking the electromagnetism module PHYC 30070, and what I want to do in this online tutorial is to discuss the solutions to assignment number 1, which was actually mainly an orientation to get you used to some of the concepts that we make extensive use of in the electromagnetism course, especially the mathematical foundations, for example vectors and vector calculus, concepts of the delta function, differential equations, and these kind of things. Okay, so let's get right into it. Let's look at the first question. Here it is. It's a revision of vector and matrix algebra, and the first part of the first question says, find the angle between the body diagonals of a cube. Okay, so as always with answering these questions, make a good sketch. Okay, so first of all, let's define our coordinate system. We will use Cartesian coordinates, x, y, z, indicated positive along these directions. So this has to be a right-handed set, which I've drawn there. And we want a cube, so let's draw a cube in this coordinate system. It doesn't have to be an accurate sketch, it has to be useful to us, that's the whole point. So something like this, and let me draw in the rear walls of this thing as well. So let's say that the origin is at the back here, O, and if I draw another point here and call that A, then that vector OA is one where you come forward by 1 unit, to the right by 1 unit, and up by 1 unit, and so that vector is 1, 1, 1. And it's a vector that goes through the cube from one corner to the other, and that's what we mean by a body diagonal. Can we make another body diagonal? Well, there are many ways to do this, so I'll just pick one way. They will all be the same because it's a cube in the end, the same up to rotations. So imagine that I draw this line, that vector here. What's that vector? Well, let's say that this point here is B, that point up there is C. What I'm interested in is the vector BC, which is of course OC minus OB. What is OC? Well, I just go up by 1 unit in the z direction, so that's 0, 0, 1. What is OB? Well, I come forward by 1 unit and to the right by 1 unit, so that's 1, 1. And no change in the z direction. So overall, the vector BC is -1, -1, 1. As I said, you could pick other body diagonals. It doesn't matter to the angle between vectors, because the angle between vectors, this is the deep reason, the angle between vectors is, the information for that is contained in a dot product, and dot products are inner products which are invariant to the coordinate system that we choose. So that angle won't depend on rotations of this system. And picking different body diagonals in a cube is just equivalent to picking different rotations of our coordinate system. Good, so how do we find the angle between these body diagonals? And furthermore, what do I mean by the angle? Well, let's indicate an angle on here, which is going to be this angle here, and I'll call that theta. So the angle between two vectors which are both sort of pointing in the same direction, so both vectors are diverging, can be got from the dot product, as just advertised. So if I take OA, and I dot it into BC, that's equal to the magnitude of OA times the magnitude of BC times cosine of the angle between them, where theta is the one that I've labelled on the diagram. Now there are other angles you could pick in this system but the one we're calculating is theta. So this is why we need to have a diagram to be sure what we're talking about. Okay, so on the left-hand side we have the dot product between OA and BC. That is 1, 1, 1 dot minus 1, minus 1, 1, which is equal to minus 1 on the left-hand side. On the right-hand side, we have the lengths of the vectors OA and BC, and both of those lengths are equal to square root 3. That's just from Pythagoras' theorem. We have the square root of the sum of the squares. And then we have cos theta, which is actually what we're interested in. And so to rearrange this equation, we have that theta is equal to arc cos of minus 1/3, which is approximately equal to 109.5 degrees. If I was talking about the other angle, let's draw it in here, this one, let's call that phi, then phi is just 180 minus theta, which is something like 70, I guess, 0.5 degrees. Good, so that's it. All of that was supposed to just be a bit of revision about vectors and dot products. Okay, so let's continue on with part B. We're given two vectors A and B that lie in a particular plane, P1. Remember that any two vectors define a plane, so the fact that we have two vectors here that are not parallel to each other actually defines the plane P1. Equivalently, of course, I could have used 3 points to define the plane. And then I have C and D, two different vectors, again, not parallel to each other, and they basically define plane P2. Find the angle between planes P1 and P2. So the thing to know to answer this question is that the angle between the planes is also the same angle as the angle between the normals to the planes. And we can easily calculate the normals to the planes by calculating the cross product of two vectors in the plane. Why? Because a plane is defined by two vectors, and the cross product is something that is mutually perpendicular to both of those vectors, therefore it must be perpendicular to the plane. Again, we begin by making a sketch. So here's my plane P1, I've just drawn it arbitrarily. Let me draw like a center line down here and draw onto this diagram the unit vector that's normal to that plane, which in this sketch I'm just going to draw emanating from the middle, and it's sort of pointing up something like this. Let me call that n1 hat, n for normal, 1 for plane 1, hat to indicate that it's a unit vector. Good. What about plane number 2? Here we are. Plane number 2 is not parallel to plane number 1, therefore it must intersect plane number 1. And you can see that there's some angle between the planes here, which I'll call theta. So this angle here that's between the two planes is called theta. Equivalently, that's the same angle theta. And also, if I draw on the normal vector perpendicular to plane P2, I'll call it n2 hat, and this is the key to answering this question, this angle in here between these two normals is also theta. So you can kind of see that it's the same angle, but if you just think about this for a little minute and think about the angles and the geometry of the configuration, you'll see that that's also the angle theta. Okay, we can calculate the angle between two diverging vectors using the cross product, as we did in part A of the question, but we need to know what these unit vectors normal to the plane are. So let's work them out. We can do it, as I mentioned already, through the cross product. So n1 vector can be given as the cross product of A and B vectors, which are given in the question. Why? Because A and B lie in a plane, the cross product is mutually perpendicular to both of them, and that's what we want. This vector n1 here is not a unit vector, but actually I don't care about that. I only want the angle in the end, so I'm not really bothered about it being a unit vector. How do I calculate the cross product of two vectors? It's pretty straightforward. I simply make a determinant and on the top I put the unit vectors along the x, y, and z direction, commonly called I, j, and k. I could put hats on them if you like, just to be very precise. And vector A goes in the second row, 1, 2, 3, and B goes in third row, 2, 5, 1. You calculate the determinant in the usual way, and in this case I get minus 13, 5, 1. You can confirm that for yourselves. Similarly, N2 vector is C cross D, which we can write in as 2, 2, 1 and 3, 2, 1. That's another vector which is 0, 1, minus 2. So there are two vectors that are normal to the two planes, and now we want the angle between them. So the angle between them we get from the dot product, n1 dot n2. As before, that's the modulus of n1 times the modulus of n2 times cosine of the angle between them, and we're interested in precisely that angle theta. On the left-hand side, we have minus 13, 5, 1, dot 0, 1, minus 2. On the right-hand side, we have the modulus of the length of the vector n1, which you have to calculate, but it turns out to be the sum of the squares of the components is 195, so you square root that. What about n2? That's slightly easier. Square root 5 times cosine theta. Inverting it, we get that theta is the arc cos of whatever that stuff is, and it turns out to be 71, let's say 0.3 degrees. If you calculated the other angle, the complementary angle, 180 degrees minus theta, that would be 108.7 degrees. That's a perfectly reasonable answer as well. Okay, so finally part C. Actually, this is extremely simple. We have a matrix product of two matrices A and B, and it's defined, so this matrix, I'm going to write matrices with this double line underneath. I'm going to take an element of that matrix, and unlike in the question, I'm going to call this matrix element ij. It's the ith row and the jth column, and the defining equation for matrix multiplication is that I take the ith row of A and multiply it by the jth column of B, and I sum over all of the components of those rows and columns. This also tells you something about the nature of matrix multiplication, which is that the length of the rows in A has to be the same as the length of the columns in B, because that's this index k that we're summing over. In fact, let me emphasize the fact that we're summing over k by drawing this in red here. Okay, so you see that the thing that's being summed over is this sort of inner indices here. Okay, very good. Now, we're not interested in M, actually. What we want is elements of F. F is a matrix which is obtained from the matrix product A times B times C. And by the distributive property, I can write this as the matrix product of AB times C, or we just did this one, M times C. And so I've reduced this to another matrix product, M times C, and we know how to do that. We've just done it above. So if we look at F, what are we looking for? FPQ we want, don't we? Then by exact analogy to the previous expression, that would be obtained by summing over, let's call it L, of the matrix M, and the components are going to be PL times the matrix C, and the components, the elements there are going to be L, Q. Fine. And we have an expression for M, and so we can write this further, more, as the sum over L. And then M itself involves this sum over K. So this is going to involve the sum over, let's draw this in red again, the A matrix with elements P and K times the B matrix element K, and this time it's KL times the C matrix, and we have L and element Q. So there we see the triple matrix product written out in component form. And you notice that all of these inner indices are contracted, as we would say. So the K is the index that's sort of innermost between A and B matrices, and that's being summed over. And the L is the label that's innermost in the B and C matrices, and that's being summed over. So everything gets summed over in this special way, leaving just P and Q on the right-hand side. They're not being summed over, and of course they're the indices that appear on the left-hand side. Okay, so let's swiftly move on to question 2. This is a revision of vector calculus, and I'm just going to focus on part A to begin with. Okay, so in this question we're actually given a bunch of information, which is extremely useful information in the study of electromagnetism. We have Maxwell's equations on the top line here. Those you definitely need to be aware of. We also have the definition of the electric and magnetic fields in terms of the scalar potential phi and vector potential A. So that's some good information that's given. In the exam, for example, this information would also be given in the appendix. That's why it's given in this question. Question A. For any general vector field psi, prove that the divergence of the curl is equal to 0. This is something that we make extensive use of in this course. So the task here is to prove it. So first of all, let's just do this in component form. Let's work out the curl of a general vector field psi. What's the curl? Of course, it depends on the representation, but let's do it in Cartesian coordinates. Incidentally, if you wanted it in some other coordinates, you can look up the representation of the differential operator in whatever coordinate system you want. Again, that's in the appendix. Good, and then we have a vector field, so it's going to have components psi x, psi y, and psi z. And here I want to calculate the determinant of this object, which you just have to go ahead and do. It's a vector, it's d psi z by dy minus d psi y by dz, d psi x by dz minus d psi z by dx, and d psi y by dx minus d psi x by dy. Okay, so I was a bit optimistic with the length of that vector there. So that's what happens when you write it all out in the usual way. And what we now want to do is take the divergence of this object, which I'll just do in one go. So let's take the divergence, here I'm writing in red, of this thing. And the divergence is, of course, just the dot product of the differential operator, dx, dy, dz, into this thing. And so we're obviously going to obtain, when we do that, the following scalar object. It's a dot product between two vectors, so the result here is obviously a scalar. So it's going to be d by dx of this bunch of stuff, d psi z by dy by d psi y by dz, and so on, plus d by dy, and so on. And the final one is d by dz of d psi y by dx minus d psi x by dy. Okay, so that looks a bit of a mess, but a lot of it cancels. So here, this first term, we have d squared psi z by dx dy, and that is something that, I'll just cross out one of the terms, that term there cancels with this one here. Very good. Then this one involving d psi y cancels with this one, and this one cancels with this one. And the reason why these cancel is because for any smooth functions, which these vector fields must be, the second mixed derivatives are equal, meaning if I take a function df by dx, d squared f by dx dy, that's equal to d squared f by dy by dx. Okay, so that all cancels out and gives 0. So equals 0, tick, that's done. Okay, so that was just a little piece of mathematics. The second part of the question, however, is onto the physics, which is much more interesting indeed. So in the first part of this, it says, use this result and the above equations to show that Maxwell's equation that the divergence of the magnetic field is equal to 0 is actually already implied from the definition of the potentials. How can we do this? We can do it easily. We take the first definition of the potential given there, which is that the magnetic field is given by the curl of the vector potential, and we just take the divergence of this equation on both sides. So we take the divergence of B is equal to then the divergence of the curl of A, and we've just proved that for any vector field, the divergence of the curl is equal to 0, and so that's it proved. The divergence of B is equal to 0. So this is nice because by using this definition of the magnetic field in terms of the vector potential, we automatically satisfy one of Maxwell's equations. Who knew? Okay, the second part says, also prove the continuity equation. Now we've looked at the continuity equation in subsequent lectures. It's about the conservation of charge, the local conservation of charge. So how can we prove the continuity equation from this formulation? Well, why don't we start with Maxwell's equation for the curl of B this time? So we'll start with the curl of B is equal to mu naught epsilon naught dE by dt plus mu naught j. This is called Ampere's law, but with Maxwell's correction. So I will start from this equation, and again, this is something that involves the curl of a vector field. So very tellingly, I can just take the divergence of this entire equation. And what do I get? Well, on the left-hand side, I have the divergence of the curl of something, so that's definitely equal to 0. On the right-hand side, I have two terms. I have, in here, some constant, mu naught epsilon naught, times d by dt of the divergence of the electric field. Now, I was able to permute the order of the spatial derivatives and the time derivatives because they're partial derivatives and they're with respect to different variables, so they commute. Good. And then this second term here is mu naught times the divergence of J. Very good. Now we're almost there. We have something that looks a bit like the continuity equation. We've got the divergence of J in it, for example. Let me at this stage already cancel this mu naught here with that mu naught there. There's 0 on the left-hand side, so dividing by mu naught doesn't do any harm there. And then I notice that the divergence of the electric field, according to one of the other Maxwell equations, is rho over epsilon naught. And so I think we're home and dry now. We have that 0 is equal to d by dt of rho over epsilon naught. The epsilons cancel, so that's d rho by dt plus divergence of J. Tick. That's the continuity equation. So lurking behind this innocuous-looking result that the divergence of the curl is equal to 0, we actually have some nice physics there. Okay, so now let's move on to part B of the question. It says, for any general scalar field alpha, prove that the curl of the gradient is equal to 0. And then we'll use that result to prove something interesting. So how do we do this? Well, first of all, let's just start from the gradient of the scalar field alpha. That's going to end up being a vector because the differential operator nabla is a vector. So it's just going to be d alpha by dx, d alpha by dy, d alpha by dz. There are no components x, y, z to alpha because it's a scalar. So the gradient is a vector. What I now want to do is take the curl of that object, which means I need to form this determinant to make the cross product. On the top, well, in the middle row, let's say, I have the differential operator d by dx, d by dy, d by dz. And on the bottom row, I have the gradient of alpha, which is itself d alpha by dx, d alpha by dy, d alpha by dz. That's some gigantic determinant which I need to calculate. I do it, and what do I get? I get a vector, because the cross product of two vectors gives me a vector, and it looks like this. Very good. And you see that term by term, each of the components is separately equal to 0. And so this whole thing is equal to 0 vector. So the 0 here is itself a vector. It's 0, 0, 0. Okay, good. So that's that. Again, the reason why this is equal to 0 follows from the fact that we have well-behaved, smooth functions, which this scalar field must be if it exists. It's a physical thing that exists in space. And then, therefore, the second mixed derivatives are equal to each other. So d squared alpha dy dz is equal to d squared alpha dz dy. Okay, good. We're asked in the second part of the question to use this result and the definition of the potentials to derive the Maxwell equation that the curl of the electric field is equal to minus dB by dt. That is known as Faraday's law. So where are we going to get that from? Let's see if I can just squash that in this bottom corner here. So let me take the definition of the electric field in terms of the potentials, which is written there at the top of the screen. We have the electric field is the gradient of the scalar potential and the time derivative of the vector potential. And therefore, if I take the curl of A, and the reason why I'm taking the curl of this equation is because I want to end up with Faraday's equation, which involves the curl of A. So I'm going to take the curl of this whole equation. That's going to be minus the curl of the gradient of the scalar potential phi minus the curl of dA by dt. Now, we've just been at pains to prove that the curl of the gradient of a scalar field is equal to 0. So it looks like all we're going to have to deal with is the second equation, which involves the curl of the time derivative of the vector potential. Again, because these are partial derivatives and because we're talking about different variables, the space variables in the differential operator nabla and the time variable in d by dt, we can commute those operators and write this second term here as minus d by dt of the curl of A. And the curl of A, we know from the definition of the potentials, is called B. It's the magnetic field. And so, putting all of this together, we have that the curl of the electric field is equal to 0 minus d by dt of B. Which, indeed, is Faraday's law. Tick. Okay, so now moving on to part C. For any general vector field psi, prove that the curl of the curl is equal to the gradient of the divergence minus the Laplacian. Okay, so that's a little bit more complicated. And the way we'll tackle this is just to do it component by component. So the first thing is we'll just look at the x component, and then we'll see that it'll just be similar for the y and z components. So let's just focus on the x component of the curl of psi. Okay, so I'll look at the curl of the vector field psi. I'm just going to look at the x component of that vector. So what's that going to look like? That's basically the following. Okay, so this is what we get. I'll leave it for you to go through the maths of actually doing those successive cross products. But this is the final result, and this is just the x component, so it's just a scalar object. So we have a bunch of second derivatives of the various components of our vector field psi. What we want to see is that this is equivalent to the gradient of the divergence minus the Laplacian. And so let's just consider those two terms on the right-hand side separately. Again, let's have a look at the x component of the gradient of the divergence. So the divergence of psi is a scalar, and then we take the gradient of it, which is a vector, and then we're going to take the x component of that. And it's pretty obvious that that gives the following. Good. Again, we just have a single component of the vector, so this is, again, a scalar quantity. So it's not looking so promising yet, but we still have another term to come. We have the x component of the Laplacian of psi, which is, the Laplacian, of course, is del dot del, which is the sum of the second derivatives. So what we want is the x component of the Laplacian of psi. What does that give us? It gives us this. That's probably the easiest one. Okay, so what we want to show is that these things are equal, and we can do that by comparing the various terms. So on the left-hand side, we have this term here, d squared psi y by dy dx. And on the right-hand side, we have the same term featuring here, almost. Again, we exploit this idea that the second mixed derivatives are equal to each other. So d squared psi y dy dx is equal to d squared psi y dx dy. So they match. What about the next term? We have minus d squared psi x dy squared, and that matches with this term on the right-hand side. Notice, of course, that in the thing we're trying to prove, it's minus the Laplacian, so it's actually minus this term, so the signs also do work out. Okay, what about the final two terms? We have d squared psi x by dz squared. That term is exactly this term. Again, noting the minus sign. And then we have d squared psi z dz dx, and that's this term. So we have minus minus, which is plus. That all works out. And then, finally, we have that this term cancels with this term because of the relative minus sign between these two things. So again, this all definitely does work out. And it's exactly the same story for the y and the z components. And I won't bother to prove that, but you can try that if you like, just to convince yourselves. So then it says, using this result and the above equations, derive the wave equation in vacuum. Now vacuum means no charge density and no current density. Rho is equal to 0, and j vector is equal to 0 vector. That's what we mean by a vacuum, there's nothing there. So how can we use this expression to derive the wave equation from Maxwell's equations and the definitions of the potentials? Well, let's see. So let's start with Faraday's law. It's one of Maxwell's equations. It tells us that the curl of the electric field can be written as minus dB by dt, and inspired by the previous calculation, let's take the curl of both sides of this equation. So on the left-hand side, we're going to have the curl of A, and on the right-hand side, we're going to have minus d by dt of the curl of B. And again, I've used this fact so that I can swap the order of the d by dt and the spatial derivatives contained in the nabla. Right, and we've got the curl on the left-hand side, and we've just been at pains to work out what that is, and so we can express that as the gradient of the divergence of A minus the Laplacian of A. That's what we've just learned. And importantly, the divergence of E from Maxwell's equations up here is equal to rho, but in the vacuum, rho is equal to 0. And so that term drops out. What else do we have? Well, we have this term involving the curl of B. What can we say about the curl of B? Well, we can relate the curl of B by one of Maxwell's equations to dE by dt plus j. And again, there's no current density in the vacuum, so that term drops out. And so this term I can write simply as, as mu naught epsilon naught times dE vector by dt. And that whole thing, I need to take minus d by dt of it. Okay, very good. So what do we have in the end? When we put all of that together, we have that a mu naught epsilon naught. Now it turns out that we know that mu naught epsilon naught is 1 over c squared, the speed of light, 1 over the speed of light squared. And then we have a double second derivative for the time, so d squared e by dt squared minus the Laplacian of E equals 0. And the Laplacian of E is nothing else but d squared E by dx squared plus d squared E by dy squared plus d squared E by dz squared. And so indeed that is the wave equation. Tick. We could equally, by the way, have started from the Maxwell ampere law for the curl of B. And what we would have found then is we have exactly the same expression, except instead of d squared E by dt squared, we'd have d squared B by dt squared. And instead of the Laplacian of E, we'd have the Laplacian of B. So in future lectures, we explore the consequences of that. And of course, what we'll find is that these wave equations are describing light propagation in a vacuum in terms of dynamical, time-dependent electric and magnetic fields. Okay, so we're nearly there now. Let's have a look at finally part D. It's giving us a position vector in three-dimensional space, r vector, in its Cartesian coordinates x, y, and z. R is the length of that vector, the modulus of r vector, and we've got to show some mathematical identities. So let's just go ahead and have a look at part I. We want to look at the divergence of R. This is dead simple. It's dx by dx plus dy by dy plus dz by dz. Each of those three terms is equal to 1, and so the whole thing is equal to 3. Okay, one-line proof. What about the curl of R being equal to 0? Okay, this takes a tiny bit more work. I should, as usual, write the curl as a determinant where, oops, that's wrong, where I have the differential operator as the first vector, d by dx, d by dy, d by dz, and then we have the actual vector x, y, z in there. And when you work it out, it gives this, which is, of course, just a bunch of partial derivatives, but given that x, y, and z are along orthogonal directions in our coordinate system, these partial derivatives are, of course, all equal to 0. We're looking at partial derivatives, and here we're looking at independent coordinates. So this whole thing, of course, is equal to 0 in each component, so this is really a 0 vector. Okay, fine. It's a pretty important result, pretty basic one to know, so it's good that we were able to prove it. And in the third one, we have something a little bit weird and takes a little bit of thought. This is the gradient of 1 over r, and this is going to be something that comes up a lot in electrodynamics and electromagnetism, because the potential for a point charge goes as 1 over r. And when we want to work out the electric field, as we can see from the expressions in this question, we have to take the gradient of the potential. So, indeed, this third one here is of physical relevance. You can do this in Cartesian coordinates to prove this relation, but it's actually much easier if we just do it in spherical polar coordinates. But to be able to do that, we need to know what the definition of the gradient operator is, this nabla symbol, what that actually is in spherical polar coordinates. Well, we can just look it up. And what we'd discover when we looked it up is that if I consider some scalar field f and I take the gradient of it in spherical polar coordinates, it looks like this. It's partial df by dr in the r hat radial direction plus 1 over r partial df by d theta in the theta hat angular direction, plus 1 over r sine theta of partial df by d phi in the phi hat angular direction. And so what we're actually interested in is the gradient of 1 over r. It has no theta and phi dependence, so right away those second two terms are gone. And then we've got to calculate the derivative with respect to r of 1 over r, and I think we can do that one. It's going to give us minus r hat upon r squared. R hat is a unit vector, and so that's also equivalent, if I like, to minus r vector over r cubed. The difference between r vector and r hat is that r hat is equal to r vector over r. Okay, so that's it, we proved it. So it's extremely simple in spherical polar coordinates. It's less easy in Cartesian coordinates, but in the end it's just straightforward algebra. Okay, so that's it for question 2. A bit laborious, but I hope you'll agree there are some teachable moments there in terms of the physics as well. So moving on to the third question, this is about the Dirac delta function and its implication in the study of electromagnetism for the concept of point charges. Okay, so again, there's some physics lurking behind the maths here. So let's have a look, first of all, sensible place to start, with question A. Calculate the divergence of the function g, which is a vector field, is equal to minus r vector upon r cubed. So let's actually write this again as minus r hat upon r squared. And we need to calculate the divergence of this. And again, it makes sense to do this in spherical polar coordinates because we have a vector that is just pointing in the radial direction, and its amplitude, or its magnitude, varies only according to the radial distance. We can calculate this divergence in Cartesian coordinates, or any coordinate system, but it will be a bit more complicated. Have a go at trying that, if you like. It is a useful exercise, but the easiest way, certainly, is to use spherical polar coordinates. And to do that, we need to know the representation of the divergence of some vector field, let's call it V, in spherical polar coordinates. And you look it up, because no one would expect you to remember this. I certainly don't remember them. And you find the following result, that the divergence of a vector field V is 1 over r squared of d by dr of r squared times the radial part of that vector field. But we're not done yet by any means. There's more. 1 over r sine theta of d by d theta of sine theta of the theta part of the vector field. And there's a more. 1 over r sine theta d by d phi of the phi component of our vector field. So this is the expression of the divergence, again in spherical polar coordinates. And again, the nice thing about this is that we only have a radial dependence to our vector field G, and so the d by d theta and d by d phi terms are immediately gone. So what we have, in fact, is simply that we can now substitute in VR as minus 1 over r squared, so in here we put VR, the radial part of the function, which in the case of g is minus 1 over r squared. So the r squareds cancel. And I get d by dr of -1, which is equal to 0. So the divergence, naively, I will say for now, the divergence of this function g is equal to 0. Okay, but there's more to this question, and it's leading us in a particular way to discover some interesting things. Let's move on to part B of the same question, and we'll see what this has to teach us. Evaluate the surface integral of g over the surface of a sphere of radius r. So we're integrating over the surface of a sphere of g dot dA. dA is the usual vector area. It's integrating over the area of the sphere. The vector in question is everywhere, at every point of the surface, it's a vector pointing outwards, normal to that surface. By convention, the vector is pointing outwards from a bounded volume. And the sphere is of radius r, centered at the origin, as convention would dictate. So what do we get? Well, because we're talking about the surface of a sphere, we can write that the vector area dA is the integral over the area in the r hat direction. We know what the unit vector normal to the surface is everywhere, pointing outwards. It's exactly r hat. And really, we should be doing this in spherical polar coordinates, shouldn't we? So let's write this in terms of r hat times r squared sine theta d theta d phi. So this is the area integral on the surface of our sphere of radius r, and we have the angles theta and phi to parameterize it. Okay, so now we're in good shape to actually calculate the integral in question. So I can write g dot r hat, and then we have a constant r squared, which I can take out of the integral, and then inside here I have sine theta d theta d phi, and what is g? G is evaluated on the surface of the integral, on the surface of the sphere, rather. And g is precisely r hat upon r squared. The r hat dot r hat is equal to 1, and so this is just going to be sine theta upon r squared d theta d phi. And that's an easy integral to do. It's just the integral of phi around the sphere from minus pi to pi, and the integral of sine theta d theta from 0 to pi, and the whole thing just gives me minus 4 pi. Note the r squareds also cancel. Okay, so what about part C? Calculate the volume integral of the divergence of g d tau over the same sphere. Now in part A, we worked out the divergence of g. We found it's equal to 0. 0 everywhere. And so if we calculate the integral of 0 over some particular volume, we will get 0. One would have thought, I say mysteriously. So I appear to have a bunch of interesting mathematical results. Well, whether or not they're interesting is a matter of interpretation, but they might seem slightly more interesting when we read part D of the question. The Divergence Theorem relates the surface and volume integrals of the types in part B and C, but it doesn't seem to work. So let's have a look at the integrals again in question. So in part B, we had the surface integral. It's the surface of a sphere, in this particular case, of g dot dA. we found this to be minus 4 pi. Whereas, if we calculate the divergence of G and then integrate it over some volume, which is going to be the volume of a sphere, then we apparently found that that was equal to 0. That's because in part A, we showed that the divergence of this function was equal to 0. So if we integrated over some volume, presumably we also get 0. They seem like two standalone results, but there is this thing, part D tells us, called the Divergence Theorem. And the Divergence Theorem tells us precisely that for some general vector field, psi, let's call it, over some volume, it doesn't have to be a sphere, any volume, if we integrate the divergence of the vector field psi over that volume, then we can convert that into an area integral of the vector field psi integrated over the surface of that volume. So whatever volume we pick on the left-hand side, it can be a sphere, it can be a rectangle, it could be anything we like. On the right-hand side, we have an area integral on the surface of that region, the surface bounding that region, and it's psi.dA, so it's a vector area. And Divergence Theorem tells us that these two things are equal. And this is exactly what we have in part D. We have this particular function g, and we find that the surface integral on the sphere is minus 4 pi, but the volume integral of the divergence of g is apparently equal to 0. So there is some mystery here. The question, part D says, why does it not appear to work? The reason why it doesn't work is that there's a problem with calculating the divergence of the function at r equals 0. Now, we blithely went ahead and just used the usual formulas to calculate the divergence of the function g, but we weren't paying very close attention to the special point r equals 0. You can see that as r tends to 0, as a limiting process, g becomes very, very large indeed in magnitude. Why? Because we're dividing by r, and r is becoming very small. So g, the magnitude of g becomes very, very large. So there's a well-defined process of making r smaller and smaller and smaller, but r equals 0, the actual point r equals 0, is not defined. We have a divide by 0 problem. So that's fine, we just have to say that the divergence of g is 0, but it comes with a health warning which says that you can't evaluate it at r equals 0, that's a special point. Fine. Now the problem comes when we try to integrate the divergence of g over a volume that includes the point r equals 0. And that's what we're trying to do in part C. So the problem here is that we're trying to integrate a function over a point where the function is not defined. And so this is why the whole thing breaks down. Parts E, F, and G of this question are to do with regularizing this integral, cutting off this divergence in 1 over r, and smoothing it out a bit, so that we can actually look at the limit of r going to 0 in a well-behaved fashion. So this is referred to as regularizing divergent integrals. And I've suggested a particular way in this question of doing that. So let's have a look in detail now at part E of this question. It says, instead of considering the divergence of g, which is actually equivalent to the Laplacian of 1 over r. Why is that, actually, before we get going? The divergence of g is equal to the divergence of, and then by question 2d part 3, we know that this itself can be written as the gradient of 1 over r. And so the divergence of the gradient is of course just the Laplacian of 1 over r. But instead of considering that, we're going to calculate the Laplacian not of 1 over r, but of some regularized function which shifts slightly the divergence away from 0. So how do we do that? So instead of considering this thing, we consider a different function, which I'll call f of r, which is 1 over the square root of r squared plus a squared for some real constant a. Now, the idea is that if I have some real constant a, then a squared is some positive number, and then r squared plus a squared can never be 0. So I'm never going to end up with a divide by 0 problem for some real constant a. Notice, of course, that r squared, with r being real, cannot be negative, so I'm never going to get r squared to cancel with a squared. So I'm good. That's what I want. Part E says, sketch f of r as a function of x at y and z equals 0 for different a. What will happen in the limit as a goes to 0? Why is this question asking us about the limit a goes to 0? Because at a equals 0, I have 1 over the square root of r squared, which is 1 over r, which is precisely the function that we started with, the Laplacian of 1 over r. So the limit of a goes to 0 recovers our original function, but for finite a, I'm going to get a regularized function. What does that look like? To be able to plot this function, we're going to have to actually calculate the Laplacian of this thing. We can see that it depends on the radial distance r only, and so again, the prudent choice would be to use spherical polar coordinates. So we need to know the representation of the Laplacian in spherical polar coordinates. I can look this up, and I will find the following. F of r can be written as 1 over r squared d by dr of r squared d by dr of our function, which is 1 over the square root of r squared plus a squared. So you see, this is not a nice expression. You have to really look this up. No one's expecting you to remember these things, or work them out even, because it's a bit difficult even to work them out from scratch. So you look up the representation of the Laplacian in spherical polar coordinates. You see that the r component of it is this. There's no theta and phi dependence, so I'm not bothering to write those. The function in question is 1 over square root r squared plus a squared, and there we have it. So I'm going to have to take the derivative of this with respect to r. So let me just concatenate all of this other stuff. So there we are. Now I've got to take the derivative with respect to r of that function. What does that give me? Minus r upon r squared plus a squared to the 3/2. And now I have to multiply by r squared and then take another derivative with respect to r. Okay, so this is a little bit complicated, but we have to do it. 1 over r squared of, and then I'll leave you to convince yourselves of the following result. We get the sum of two terms because, of course, we have an r cubed on the top and then something else on the bottom that depends also on r. So we get this nice result. And with a bit of manipulation, namely by multiplying the first term by r squared plus a squared, top and bottom, and then adding up those two terms, because we've now managed to standardize the denominator, it actually turns out that this whole thing is equal to minus 3a squared over r squared plus a squared to the 5/2. Okay, that doesn't look like a particularly nice function, but that's the correct answer. So this f of r is given by this thing. So the whole point of this is that we can approximate the divergence of this vector field r hat upon r squared, which in the end, of course, is supposed to represent the electric field due to a point charge. We can approximate that to this function f of r. Good. What does this function f of r look like? Let's plot it. Okay, so the idea is to approximate the divergence of r hat upon r squared by this function for some particular value of a. Let's see what it looks like when we sketch it. So I'm actually going to plot minus f of r as a function of x at y equals z equals 0. So this is a particular cross-section, if you like, through the surface of f of r, but it's perfectly representative. In fact, it has spherical symmetry, so it doesn't really matter. So what does this function look like? Well, at very, very large magnitude of x, the denominator becomes very large of f of r, and that suppresses the function. However, at r equals 0, f of r is equal to minus 3 upon a cubed. Now, minus 3 upon a cubed is finite, and we don't have any divide by 0 problems if we have some real constant a which is greater than 0. So this is doing the trick. This is exactly what we want. However, we can also see from this that if I set r equals to 0, and then I take the limit of a goes to 0, then f of r goes to minus infinity. So there's a problem there. This is the divergence problem that we had before. So how does that look when I sketch it? Well, let's consider a smaller a. I see a function that looks like this. So it's more strongly peaked around 0, but still finite. And indeed, if I were to consider it even smaller a, you would get even narrower, but even higher, and so on. So this function that we've come up with here, this f of r, is actually a representation of the delta function, the Dirac delta function, or the delta distribution, you could call it more properly, because it is something that is well defined for some real finite value of the parameter a. As we make a smaller, the distribution becomes narrower and narrower and narrower around r equals 0, and the distribution becomes higher and higher and higher. There's one other property of the delta distribution that we need, which is that when you integrate it, it integrates to 1. So we need to check that that actually is a property of this function. What happens to this function when I integrate it? And that's actually part f of the question, to actually go ahead and integrate this function. So here we have it, the integral over all space of f of r d tau. D tau is the volume element. Of course, it makes sense to do this in spherical polar coordinates as usual. And so we'll end up with this function. Let's do the radial integration of the function that depends on r. And then we have the angular integration over theta and the angular integration over phi. And that whole thing, the angular integrals give me 4 pi, and I'm going to multiply that by an integral which I'll call I. And we need to find this remaining integral I, which is this radial part of the integral. And this expression that I've written down here is just following from the fact that in spherical polar coordinates, d tau is r squared sine theta dr d theta d phi. So we need to calculate this integral, which I've called I. Let's do it by parts. There is probably a much simpler and more elegant way of doing this, but this is kind of the most obvious way. Let's just go ahead and do it by parts. Let's suppose that something called dv by dr is the factor minus 3a squared r over r squared plus a squared to the 5/2, whereas something called u can just be r. If dv by dr is this object, then v itself is the indefinite integral, which is an easy one to do, and that's because, cleverly, I chose there to be a factor of r upstairs in this factor. If u is equal to r, then du by dr is just equal to 1. And so I can use integration by parts, which tells me that the integral I is u times v minus the integral of v du by dr. And that gives me the following. We have a definite piece, which is u times v, which is integrated between 0 and infinity. And then I subtract off the integral, again from 0 to infinity, of v du by dr. Good. And this integral we can analyze. This first term, when r goes to infinity, downstairs we have something that's very, very large. It's basically r cubed, and as r goes to infinity, and that kills the contribution. Whereas r equals 0, downstairs is finite, whereas upstairs is equal to 0. So the whole thing is 0. What about this second term? This another integral that we've got to do. It's not yet easy. Let's suppose that this a squared can be written as a squared plus r squared minus r squared. Well, we don't have to suppose very hard, that's definitely true. So when we write the integral, therefore, we can write it as minus the integral of 1 over r squared plus a squared to the 1/2. Why? Because I've divided out the factor of r squared plus a squared. But that's not it. I have this counter term which I need to put back. And this is, again, something that we need to solve by parts. So let's suppose that dv by dr is equal to r over r squared plus a squared to the 3/2, whereas u is equal to r. This tells us that v, by integrating, very similar to the previous expressions, simply this, whereas du by dr is, of course, just equal to 1. And so this integral that we're investigating here is further reduced. And now we see something rather interesting happens, because this second integral here, the integral of 1 over the square root of r squared plus a squared dr, that term actually cancels with this term all the way back here. That one has a minus sign, this one has a plus sign. And so, in the end, we're left with the result that this integral I that we're looking for is actually just minus r upon the square root of r squared plus a squared, evaluated from 0 to infinity. What happens at infinity? At infinity, the object downstairs is the square root of something large squared plus a squared. R will be large compared to a as r goes to infinity, so we can throw away the a, and the square root of r squared is r. That cancels top and bottom and will give me minus 1. That's a limit. Whereas when r is equal to 0, downstairs is finite and upstairs is equal to 0. So that's it. The integral is equal to minus 1. Now this integral I is not quite what we wanted. If you recall, what we were really after was the integral of f of r d tau, which was equal to 4 pi times the integral I, which we now discover is minus 4 pi. And the important and miraculous thing about this calculation is that the integral over all space of this function is minus 4 pi independent of our parameter a. So I can pick a to be large, in which case I have a very smoothed, broadened function, or I can pick a to be very, very small, and it would give me a very sharp, highly peaked function around 0. And the integral, independent of that, is the same thing, and it's equal to minus 4 pi. And that means that I can use this function as a good approximation to the Dirac delta function, because as I take the limit of a goes to 0, it picks out the function, the value of a function at r equals 0, because the function is very close to 0 when you're away from 0, but it's very, very large when r is close to 0. And it's a good distribution, a kind of probability distribution, if you like, because it has a conserved integral. The weight under the curve is the same. So as I send a goes to 0, it becomes like a pole, a delta peak. But the integral under that pole is still the same, minus 4 pi. So let's just summarize this information. We've defined a function f of r, which is the Laplacian of 1 over r squared plus a squared, which is something that should give us, in the limit of a goes to 0, the Laplacian of 1 over r, which is exactly what we wanted. This thing is actually equal to minus 3a squared over r squared plus a squared to the 5/2. So that's the actual function that we're looking at. And this function has several important properties. Let's actually call this function a function f of r and a. We'll parameterize it both by the r and the a. It has some interesting properties, as we've just deduced, that f as a function of r as a goes to 0 is equal to 0 when r is not equal to 0, and it tends to infinity as r approaches 0. So that means that it's picking out the value of the function as r goes to 0. The second property is that if we integrate f of r and a over all space d tau, I get minus 4 pi for all a. And these two properties together are telling us that f of r and a is a good description of a delta distribution. It's a good, well-controlled, regularized version of the delta distribution. Now, f of r and a goes to 0, therefore tends to the Laplacian of 1 over r as a goes to 0, and therefore Laplacian of 1 over r is minus 4 pi times this delta function of r. We just get the extra factor of minus 4 pi there because the definition of the delta function is that it integrates to 1, whereas our f of r and a integrates to a factor of minus 4 pi. Okay, so now finally we're in a position to show that the divergence theorem is satisfied as it must be. Let's calculate the volume integral of the Laplacian of 1 over r d tau. This time we're aware of the divergence around 0 and we're taking care of it using this delta function. We're integrating over a delta function which collapses the integral to the r equals 0 value and just picks out a factor of minus 4 pi. And of course, this is exactly what we wanted. So finally, what's the implication of all of this for electrostatics? This is part H, the final part of this question. So let's write down the Coulomb law for the electric field due to a point charge q sitting at the origin. We have that E, electric field, is equal to the charge q r hat upon 4 pi epsilon naught r squared. This is Coulomb law. For a point charge q at the origin. Good. Let's use Gauss's law and express the field flux through some surface in terms of the divergence of the electric field integrated over some corresponding volume. So that would be equal to q over 4 pi epsilon naught of the volume integral of the divergence of r hat upon r squared, integrated over some volume d tau. And we've just learnt something about that divergence of r hat upon r squared, namely that this thing is equal to 4 pi times the delta function. And therefore, on the right-hand side, the 4 pi's cancel, and we have q over epsilon naught of the volume integral of the delta function d tau. But on the left-hand side, we use Gauss's law to relate the electric field flux through this surface to the charge enclosed, divided by epsilon naught, which, of course, is equal to 1 upon epsilon naught of the charge density, d tau. So the charge enclosed is the volume integral of the charge density. That's what we mean by the charge density. And so what we have here is a relation between the charge density on the left-hand side, which produces the electric field, but then on the right-hand side we have a volume integral which just contains the delta function. And this volume can be over any size, any region, and therefore we can extract that the charge density is Q times the delta function. It's a single point charge located at the origin. Which is, of course, correct. So that's what we know the electric field in Coulomb law is relating to. So what we see here on the right-hand side is that we're integrating the delta distribution over some volume, and that just picks out the value of the integral at r equals 0. And that, of course, is where all of the charge must be located. It's really a point charge. Okay, so on to the last question of this assignment. This is a bit of fun. It's on the magnitude of the electric forces, and it's making a comparison between the inverse square law for electrostatics and the inverse square law for gravitation. Of course, we know that there are some differences. Of course, gravitation is mutually attractive. There's only one kind of matter, if you like, and matter attracts matter. In electrodynamics, we have positives and negatives, and like charges repel, and unlike charges attract. Also, there's a difference in terms of the magnitude of those forces, and that's the content of this question. So in part A, we're asked, what would the mass m of a proton have to be if the gravitational force between two protons at rest were equal to the electric force? How does this compare with the actual proton's mass? Okay, so let's have a look first of all at what the gravitational force between two protons would be. It's an inverse square law, so we have m squared times capital G, gravitational constant, divided by r squared. It's an inverse square law. Whereas for electrostatics, we have q squared, the charge squared, divided by 4 pi epsilon naught times r squared. So if the forces were equal, then obviously Fg is equal to F electric, which leads to the condition that m squared g must be equal to q squared upon 4 pi epsilon naught, which in turn tells us that the mass m must be 1.9 roughly times 10 to the minus 9 kilograms. 10 to the minus 9 kilograms, that sounds very small. However, it's actually 10 to the 18 times the actual proton mass. So the mass of the proton would have to be absolutely massive compared with its actual value in order for the gravitational force to be anything like comparable to the electric forces. Okay. Simple calculation, but kind of instructive. Part B. If two coins were placed 10 meters apart, what would be the force between them if, for some reason, their nuclear and electronic charges were unbalanced by about 1%? So the idea here is we imagine some fantasy world in which we have a metallic coin, but that for some reason there are more electrons in the coin than there are protons, and therefore there's a charge imbalance. Of course, in the actual world, atoms are overall charge neutral. There's the same number of protons as there are electrons, so everything nicely balances. But here we're assuming that there are more electrons than there are protons. So let's assume, as it asks us to do in the question, that these coins are made out of silver, and that they have a mass of 2.5 grams. Okay, so first of all, 2.5 grams of silver. How many electrons are actually contained in such a thing? Well, silver has atomic number of 47 and a mass number of 107.6. 0.86 if you look it up. So 1 mole of silver atoms will weigh, by definition, 107.86 grams, which means that 2.5 grams of silver is 0.023 moles. And that means that it's 0.023 times 6.022 times 10 to the 23 silver atoms. Because here I'm using that Avogadro's number is the number of atoms in a mole. So what we know is that 2.5 grams of silver is equivalent to 1.396 times 10 to the 23 atoms. And then we have to multiply that by 47, because that's the atomic number, to get the number of electrons. 6.56 times 10 to the 23 electrons. Okay, so our coin, so an actual coin of silver has something like 6 times 10 to the 23 electrons in it. It's pretty massive. So now we'll assume that there's a 1% charge imbalance, which means that the overall net charge, Q, is 1% of this number, which is 6.56 times 10 to the 21 electrons. So this is still an enormous number, even though it's only 1%, it's still an enormous number, and if we convert that into coulombs, we find that that is 1,050 coulombs. So the force between two such coins, 10 meters apart, is basically the Coulomb force between two point charges, each with this value of Q, which is 1,050 coulombs, separated by a distance of 10 meters. So what is that force? F equals Q squared, so a Q that we've just worked out, divided by 4 pi epsilon naught r squared. The r is 10 meters. And that gives me 10 to the 14 newtons. That's a massive force. That's the force equivalent to the entire mass of the Earth times the gravitational constant at the Earth's surface. So it's the force between these two silver coins of 2.5 grams of silver each, if we had a 1% imbalance of charge in these coins, would be enough to lift the weight of the Earth. Okay, so all of that is just to illustrate that electric forces are pretty strong in comparison to gravitational forces. Okay, so on to the last part of the question, part C. Make a rough estimate of the work that must be done against electric forces to assemble a uranium nucleus from two equal halves. And here we're to assume that the uranium atom at the end consists of just two adjacent equivalent spheres. So the idea is we've just got two spheres and we're bringing them together, and we want to know what the work must be done against electrical forces to assemble this uranium atom. And the idea here is it's some kind of crude approximation for the process of nuclear fusion. Okay, so how does that work? Imagine that we have a uranium atom which has a mass number of, as everyone knows, 238, and we have an atomic number of 92. So if we have two halves initially, then they would have a mass number of 119 each. And that, of course, corresponds to tin. So what we're imagining here is we're bringing together two tin atoms to try to make a uranium atom by a process of nuclear fusion. So just in pictures, the idea is we have two tin atoms, and we need to bring them together to a distance d. And this distance d is going to be half of the nuclear diameter of the uranium atom. And that turns out to be 15 femtometers, which is 15 times 10 to the minus 15 meters. So of course it's incredibly small. So we're assuming that the centers of the positive charge of the two tin nuclei are going to be 7.5 times 10 to the minus 15 meters apart. So half of that nuclear diameter of uranium. Of course, this is an approximation, but this is just a ballpark figure that we're trying to come up with here. So what we want to do is work out the work done to bring these nuclear halves of these two tin nuclei from very far apart, r equals infinity, to this distance d equals 7.5 times 10 to the minus 15 meters. So the work done to assemble this uranium atom against these electric forces is the line integral from infinity to d of the force dr, and that force in question is of course the Coulomb force, and when we work that out it's just going to end up being q squared over 4 pi epsilon naught d. That's the work done. And when we plug in the value of q here, which is 92, the atomic number of uranium, divided by 2 times the electronic charge E, that is 7.36 times 10 to the minus 18 Coulomb, a small number of Coulomb this time. And so finally we have that the work done ends up being, when you plug all the numbers in, 6.5 times 10 to the minus 11 joules per atom. And of course, that's the key to it. This might seem like a small number, the work done is 10 to the minus 11 joules, but this is per atom, and therefore, if we want to know how much work is done per mole, we multiply this by Avogadro's number, which is 10 to the 23 or so, and that will of course correspond to a mole of uranium atoms, which is 238 grams. And if you want to know what's the energy content is per kilogram, then we can convert that into joules per kilogram. And we find that this is 1.64 times 10 to the 14 joules per kilogram. So that's obviously a very large number of joules of energy stored in a kilogram of the uranium there. That's, if you want to convert it into something more meaningful sounding, that's also equivalent to 4.6 times 10 to the 7 kilowatt hours per kilogram. A kilowatt hour is 3.6 times 10 to the 6 joules. So this is a very, very large amount of energy stored in each kilogram. Okay, so that was the end of assignment 1. I hope that was instructive, and I think we've been through these questions quite thoroughly, but if there are any further questions, then don't hesitate to contact me.